Hello, everyone, and thanks a lot for being here. I'm very excited to tell you today about the interactive animation that we made on level curves and directional derivatives. The interactive animation is a rather new approach. It's the first time we did it. And in this talk, I'm going to tell you about the need for this animation, this interactive animation. And of course, I'm going to demonstrate it to you. I'm going to show you how we use it in teaching. And I'm also going to let you in on the creative process and give some peeks of the making of. But first, an introduction. My name is Vera. I'm from the Delft University of Technology. And I work at PRIME. The acronym was already spoiled, Program of Innovation in Mathematics Education. We need to hear it a couple of times before you remember anyway. We're a program at the university that innovates the mathematics courses for engineering students, in particular the mathematics courses they have in their first year, which are really the primer. And in one way in which we're innovating them is by making visual materials for in the lecture and to practice with. And we do this with the visuals team. That's us. The visuals team consists of lecturer representatives, master students, and coordinators. Many of them are here as well. This is me. I am a master student in computer science, but I also have a bachelor in fine art. And my function in the team is as visual expert. But today I'm speaking on behalf of the entire visuals team. So far, the introduction. I'm going to now show you what we make and why there is a need for an interactive animation, which sort of naturally arises from that. Because with the visuals team, we make visualizations and animations of mathematical concepts, especially for courses in calculus and linear algebra. And I actually make most of the animations, like this one, which is it's an illustration of solving a linear system. And in animation, you have some perks over a static image. You have the opportunity to move things around and sketch complex scenes. But you also have control over the exact angle in which you do this, and also the timing of the movements. And in addition, you can provide a narrator which actually explains what you're seeing, which in quite abstract concepts is very beneficial. Because in this visualization, the planes that you see correspond to a row in the system. And when you add one row r times to another, depending on the amount, on the value of r, the plane will rotate on an axis. And if you don't know that, this looks still cool because it's beautiful. But it's not super informative. So this control over the varying of the parameters and the ability to provide an explanation is a very powerful thing of animations. But we want students not to just consume stuff. We want them to engage as actively as possible with the material, because yeah, the more you engage with the material, the better you will learn. So we make also something that we call applets. These are small web-based programs in which you have visualizations that you yourself can move around. There's no timeline, no nothing. And some people know these things as mothlets. And this is an example of calculating with complex numbers, some operations on them and what that means geometrically. That's one we made. We also made one where you inspect the image of a linear transformation. And then as a student, you can just drag parameters around, do different views. But ideally, you provide the student with some extra information on what is going on here. So that's something we struggle with. Ideally, you give them an explanatory animation and then have this. That's something actually we did. the animation I showed before that, that is followed up by an applet that students can interact with. So first they have it explained, and then they can go on and explore and engage actively with this. But it's not very ideal, right? It takes a lot of work to make. We have two people working on different projects. And as a student, you also have to switch the mediums. So we were toying with the idea of combining this for a while. And then we got a good case for that, namely this topic of level curves and directional derivatives. Teachers came to us and said, well, we would like your help with this. And it's excellent because this topic is very suitable for visualization. As you can see here, this is a screenshot of what I'll go demo later. But you see already here, you have a 3D plot and you have two corresponding 2D plots. If you were to draw this in a lecture, it would take forever and you have to be very precise. And then when you're done drawing, you can't even turn it around to show the other part. So lecturers really wanted something interactive so they could quickly adjust also to questions of students. And it would also be beneficial for students so they can use it at home. But at home, you want them to have this extra explanation, or in case they missed something, they can rewatch it again. So it's a perfect opportunity to combine the interaction with the animation. And so we made it happen. And since this is not a thing that has been done a lot before, I'm gonna first now give you the demo so you have a clue of what I'm actually talking about. I'm gonna switch my view now. And it goes quite smooth. I hope you can all see this website here in which I've put several parts of the animation together. Because we split it up in 4 parts. One is introducing level curves, one is introducing directional derivatives. Then there's one that explains the relationships between the two. And we have also made a bonus one on gradients. But I'm gonna start with the first part on level curves. In this, we explain the plot from 2 variables and how you make a contour plot from them. And we start with just quite a regular 3D plot of a function of 2 variables in which you can move it around, zoom, pan, do things you do with a plot in 3D. And then you can change the function. I just discovered that it does cosine and sine. You see? And I was gonna ask the audience for a favorite function of 2 variables, but it seemed a bit too risky. And so I figured out my own favorite one, which is, this one gives nice contour plots. And we're gonna now leave it to the narrator to explain how that works.
The intersection of the graph with the horizontal plane consists of all points with the same value of the function. Projecting this curve back to the xy plane, we obtain a level curve. If we change the height of the horizontal plane, we get a new intersection for a different value of the function. Thus, we also get a new level curve.
I'll pause it again here. Lots of additional elements have popped up in the screen, and many of them are also interactive. So this 2D plot here, you can zoom or move it around, find intersections, stuff you do with a 2D plot. And in the 3D view, which you can still move around, we also have now a draggable plane to adjust the level curves. You can see them again. You can do it here, but we also made a slider. And we provided the option to add some contours to make your own nice looking plot. There you go. I said it was nice. And you can also clean them up if you made a mess. That's the part which explains this relationship. I did a lot of it now. She also explains some interactions. And I'm going to show you then the second part to show how it works with more multiple views. Because to explain the directional derivatives, you need a lot more. And then the narrator will introduce these views one by one. And they are all still also interactive. So here you can zoom, move them around, more sliders to play with. We also have a draggable element here. And what I haven't shown yet, I've so far only done stuff while it was paused. And this is what you do if you explain it to someone. But you can also have this interaction while it's playing. I'm going to turn off the sound, otherwise you have us babbling through each other. And then show you that while that's animating, I can still zoom in here or rotate this around. I can basically have all interactions except with the elements that are being animated at that point. And finally, any adjustments that we have made at any one point will stay for that during the entire timeline. I can also just skip through, and you see that this plot remains zoomed in also earlier in the video, except if it's an animated parameter, of course. So I think that's quite an impression. I'm gonna highly recommend you explore it yourself, of course, and at the end we'll share links. It's much more fun if you get to do it yourself, so my role is the most fun here. But you've seen the main idea of the interactive animation. You can interact with many elements while it's paused or playing, and I'm going to show you how we work with this in courses. Back to my slides. There. Well, we finished them this year, and so far all of our lectures have been online. So here's a screenshot of how we use it online in a class where teachers explain these concepts, how it works. They of course use it while it's paused because they're capable of picking the right angles and explaining it themselves very well. So it's in lectures, and then after lectures, students can use it at home, and we've made one of our lecture representatives made homework exercises where you're encouraged to first watch it, and then you can answer questions about insights that you hopefully obtained. And we do this in a graph pull system, which also gives feedback if you misunderstood. So we use it in lectures and in homework exercises, and so far it's been piloted in calculus courses for nanobiology students as well as aerospace engineering. And we heard that students appreciated this a lot. They said they would much quicker grasp the concept, and teachers also appreciated the ease with which they could show for different situations or different functions, and skip all this plotting that I said. In this academic year, we're going to roll it out in all of our calculus courses who treat this topic. So it's going to be university-wide, which is very exciting. And we also have a research team that's going to evaluate the outcome of this on learning, but that's something that we're still investigating. So that's how we use this at the TU. And then I'm going to use the remainder of this talk to let you in on the creative process of making this, because that was actually, it was a technical challenge, but there was also a lot of creativity. And if you want to make something like this yourself, I think there are many things that we did that might be nice to know. So there we go. we first start by selecting a good topic. I've already told you why this particular topic is so suitable, but more in general, topics that would be suitable for an interactive animation are mathematical concepts that have at first a geometric interpretation that's meaningful, otherwise there's not much to visualize. But it should also be a topic that you want students to explore on themselves and that is complex enough to require additional explanation. For good ideas, we strongly rely on our mathematics teachers because they're experienced and they know all the really interesting cases that you haven't already seen. So they gave us this great idea. And the first thing we did with that was write the script. I've dug into the archives to find the first script for you with the first revisions. It says very first alpha version here. And the script just details everything you want to tell and also notes the most important things to show. And then from that, the storyboard is made. That was me. You don't have to be able to draw very nice to do this. The important part is that you convey to the developer also what is going to happen and to make sure that everybody is on the same page. And then comes sort of an iterative part in this stage where you have the script and the storyboard. You're going to make some design decisions, especially for the narrative. What do we show and what do we tell, and in which order are which elements introduced? For us, that was very iterative. We first made the script and then the storyboard, and then we revised the script with the storyboard, and we revised the storyboard with the revised script. And then finally, the script was also made more into speech language, so it was easier for the narrator to read it aloud, and also more attuned to the student's language. So there we are with a script and a voiceover and a storyboard. That was the real fun still has to begin because we only have to, make the whole thing happen. And it was a challenge because there are no frameworks that provide you with the tools to make an interactive animation. We found an example online, but it was completely undocumented and also said, well, this is not really something we would like to share with the world, how we did it. So we had to figure this out ourselves. And we are super lucky to have Saira on the team, who is here as well. And she figured out how to set up a combination of these frameworks, React, GSAP, and 3JS, in a quite reusable way, which we could also extend. I have documented the code, and I think it's very feasible to work with this on another project. And if anyone here is interested, we can share some of the code demos that I made for the documentation. Just skipping over, we made it now. Saya found the magical framework, or she just set it up, and there we have the first version of our animation. And you think we're almost there, going over all these steps, but this is really where we did this cherries on top, because in the screen we had already set points of interaction. But when we were playing around with this first version, there were many points that, you want, there's this point P and I really want to drag it, but we hadn't done it yet. So we noticed there were more of these spots, and we did some user studies with the students to find more of them, and integrated also this feedback. And we also did some tuning to the layout, because some functions turned out during the user studies to be much more important than others, and some plus could be made much smaller. And that's how we arrived at this final layout that you also saw in the demonstration with the same, with all these interactions. And there it is. it's done in the 4 parts that I just showed you. So that was quite a lot. I've told you a lot of things that I'm just going to recap quickly. We started out with the observation that there are mathematical concepts that you can visualize with both an animation and an applet, and that the combination of the two in an interactive animation can be the preferred approach and very well justified. I've demonstrated our results on level curves and directional derivatives, and shown that you can interact with many elements while the animation is paused or playing. I've also shown you how we use this at the university in courses by embedding them in lectures and with extra homework exercises. And I've shown you a peek of the design process and some of the decisions that were made there. We're currently in the process of storyboarding and scripting for the next one on Lagrange multipliers, and we're ourselves also eager to see how well this pipeline will work for another topic. I would like to thank you all for your attention and listening. These are our contact and link to our portfolio, where you can find the interactive animation, as well as all the other applets and animations that we've made. And then if you have any questions, we are of course happy to take them.